All right, so welcome back. I'm glad to have you again for this new presentation. So we are now going to talk about Juniper load balancing. So specifically, we're going to talk about OSPF, ISIS, and BGP load balancing. But before we get into the details of how to enable load balancing for these protocols, I want to do a review of the concept of the routing table versus the forwarding table. And I'll explain why I want to talk about this in the context of load balancing. So the routing table versus the forwarding table, here's the idea. In all Juniper platforms, in all Juniper devices, there is a clear separation between the control plane and the forwarding plane. It's been like this since the beginning of Juniper, since the very the very first products that Juniper released. There's a control plane that is handled by the routing engine and a packet forwarding engine, or actually the forwarding plane or data plane, which is handled by the packet forwarding engine, which is basically your line cards. Depending on the model, depending on the type of platform that you're working with, the routing engine is going to be a card that you install in a particular slot. It could be a virtual machine running on top of your device, QFX, for example. The routing engine is a virtual machine. And the packet forwarding engine is basically the ASICs that, forward the traffic when it arrives. So the routing engine controls the device and is responsible for exchanging routing information and building the routing table. So whenever you turn on a routing protocol, OSPF, ISIS, BGP, or you configure static routes, or you add IP addresses to the interfaces, and that results in local or direct routes, all of that information goes to the routing table. So the routing table, or the routing engine, looks at all the information in the routing table, compares all routes for the same destination prefix, and chooses the best routes. So for example, if there is a route for 10.1/16 that was learned from OSPF, and another route for that same prefix, 10.1/16, that was learned from BGP, the OSPF route is going to be chosen based on the preference value. So that route becomes active, and it's going to be installed in the forwarding table. So you can think of the forwarding table as a subset of the routing table. Now, the forwarding table is, or a copy of that forwarding table is going to be placed in the packet forwarding engine. And when traffic arrives, the packet forwarding engine, it's going to be looking at the local forwarding table to make forwarding decisions. The packet forwarding engine is in charge of all the processing of traffic when it arrives, applying class of service, policing, packet filtering, all that is implemented in the PFE. So again, when traffic arrives, the PFE looks up the destination address on the local forwarding table and makes forwarding decision based on that. That traffic, which we call transit traffic, never goes to the routing engine. At this point, you might be asking yourself, why we're talking about this? Well, I thought we were talking about load balancing. Well, the reason for that is that by default, only one next hop per route is added to the forwarding table. In that process, where the routing engine chooses the best route in the routing table, only one next hop for each one of those routes, it's going to actually go to the forwarding table. And because the PFE has a copy of that forwarding table, there's no load balancing by default. So even if I have multiple routes, let's say BGP routes, or I have multiple next hops for my OSPF routes, only one of those, it's going to be in the forwarding table, and only that one will be used for the actual forwarding of traffic. So the next question is, how do I change that? Well, what we're going to do is configure a policy, a routing policy. And I know that Dan, for example, was here this morning. We were talking about policies. We are going to apply this policy between the routing table and the forwarding table. And it's going to be an export policy because we're exporting those next hops from the routing table into the forwarding table. So this policy is going to have an action of then load balance per packet. And that's what's turning on the load balancing process. So right after you configure this policy and apply the policy between the routing table and the forwarding table, you will see that the forwarding table now contains all the multiple next hops available to reach that specific prefix. And that, again, it's on the PFE. So when traffic arrives, the PFE does a route lookup. It finds that there is 2 possible next hops to reach that destination. And in order to choose one of the 2, it hashes source address, destination address, protocol number, port numbers, and so on, depending on the configuration. And the hash determines which one of the 2 next hops is going to be used for that particular flow. So the PFE implements per flow load balancing once the policy has been applied. So I was talking about these in my earlier presentation. So this is representing the, that's a concept of routing policies. But we're going to focus on the, what happens between the routing table and the forwarding table. So we're going to apply an export policy to enable load balancing. Again, it's an export policy because it's from the routing table into the forwarding table. And policies are always applied from the point of view of the routing table. Quick review of the syntax of a policy. We go under edit policy options. In this case, we're doing edit policy options, policy statement, the name of the policy, which you call it whatever you want, then term and the name of the term. And inside that, we're going to have from statements and then statements. The from statements defined the matching criteria. In this particular example, I have 4 different matching conditions. From protocol aggregate and from protocol static are matching on the same attribute protocol. Therefore, the route has to be either static or aggregate to match. And then I have a couple of route filters, so the route has to match either one of these route filters. Now, the actions here are accept, next hop self, which is used when we have to fix the next hop of the BGP route. You can add communities. These are just examples. But here is the one that we're going to use to turn on load balancing. I can have a very simple policy that doesn't have any from statements, doesn't have any other actions. The policy just says, set then per packet load balance, and then I apply that. And every time there is a route with more than one next hop, load balancing will happen. Or I can be more specific. Maybe I want to apply load balancing only to certain protocols or only to certain prefixes. So I can just add some from statements to make that happen. And I'm going to show you some examples where you can see the 2 options, basically. All right, so now that gives you an introduction of how this works. Let's take a look at some examples. I have examples for OSPF, ISIS, and BGP. So in OSPF, here's my topology. And basically, I have a couple of interfaces connecting these 2 routing instances. They have their own loopback interfaces. Here's a config of the interfaces, nothing fancy there. And I have a routing table, a routing instance that it's running OSPF. And for now, I don't have load balancing enabled. So I check that the neighbors are up, and then I take a look at the routing table. So what I want you to pay attention to here is that VSRX1 is receiving, or this routing instance is receiving 5 different routes, 5 different OSPF routes from the neighbor VSRX2. And So, I mean, for each one of these routes, because of the topology, I'm going to have two possible next hops, 10.10.111.2 and 10.10.112.2. So you can see that for each one of these 5 routes, I have the 2 next hops available. However, for each one of the routes, you see that there is a route that has that greater than symbol, and that's indicating that that next hop was selected for that particular route. And that selection actually happens at random. So you see that for some prefixes, for some destination prefixes, I'm choosing, or the router chose 11 or 111.2, and for some other prefixes, it chose 112.2. You can also check the contents of the forwarding table. Show route forwarding table, and then I'm saying table VR110. I want to see only that particular routing instance. And you can see that there is only one next hop for each one of those routes. And it matches the next hop that has that greater than symbol. So there is no load balancing happening right now. So we'll go ahead and create some policies. I created 2 just to show you some examples. You don't have to do more than 1. So these policies under edit policy options are called low balance all, and the other one's called low balance some routes, just to give an idea what they're trying to do. So the first policy is very, very simple. It has one term that just has the action, then low balance per packet. It says per packet. It's kind of because of legacy reasons. In the past, the chipset of the routers only supported per packet load balancing. Eventually, the newer chipsets could do per flow load balancing, but they never changed the command. So this is actually doing per flow load balancing. So now we have to apply the policy to the forwarding table. So we do edit routing options, forwarding table, and then set export and the name of the policy. So I'm going to show you the results with the second policy. And I didn't mention the details about that policy, but this policy has not only the action then load balance per packet, but it also has from route filter 200/8 or longer. So I'm being very specific on the prefixes that I want load balancing to be applied. So I'm applying that policy to the forwarding table. Once again, it's an export policy because I am copying this route from the routing table into the forwarding table. So from, it's an export. So once I apply this, obviously I need to commit my configuration. I take a look at the routing table again. And if you compare these with the output of the previous slide, there's absolutely no differences. Nothing changes in the routing table. What changes is what the router is going to now place in the forwarding table. So you can see that for 200.110.110/24, 200.110.110.1/32, for those 2 routes and only for those 2 routes, now I have 2 next hops. So the PFE, every time there's a packet going to this network, the PFE will hash the source address, destination address, and so on, and pick one of these 2 next hops. So just for comparison, this is how the routing table or the forwarding table looks like before, and this is how it looks like after. And actually you can see that the routing table doesn't change at all. Now, let's go ahead and apply the other policy, load balance all. And here's how that forwarding table looks like now. So for each one of those routes that has 2 possible next hops, I actually have the 2 next hops in the forwarding table. So I'm going to be doing, or the router is going to be doing load balancing for any destination for each one of these prefixes. All right, so actually in OSPF, it's just a matter of having, routes with the same total cost, or let's say a path or multiple path with the exact same total cost, and then enabling load balancing. So there's not much else that you can do or that you need to do to make it work. ISIS is very similar to, I built a similar topology. It has the loopback with the ISO address. So what I did is, since I had the policy activated before, I deactivated the policy so that you can see the difference. So here's again how the routing table looks like, and it's pretty much the same idea. I have my 5 different prefixes, and the router is choosing randomly which one of the 2 next hops is going to be used for each one of these destinations. And when I look at my forwarding table, it's the same. I have only 1 next hop for each prefix. So I go ahead and activate the policy, and I commit, and here's how your routing table looks like. In this case, I'm using that policy that activates load balancing for all the prefixes. So nothing more, nothing different between OSPF and ISIS in terms of how you do load balancing. Now, ISIS does have, and this is, let's say, relatively new feature. ISIS has the ability, or let's say Junos have implemented this new feature in ISIS that allows load balancing between unequal links, unequal bandwidth. It's called weighted ECMP. ECMP stands for equal cost multipath. In fact, let me go back for a second. This is equal cost multipath. This only works when you have routes with the exact same metric, with the exact same cost in OSPF and ISIS. So the idea of weighted ECMP is that if you have a situation where you don't have the same bandwidth, you can still load balance the traffic, and you want that load balancing to happen proportional to the bandwidth that it's available. Now, it's for very particular, let's say, topologies that this is going to help you. So imagine that we have a network, a situation where there is a couple of routers connected using lag interfaces. And each one of these lag interfaces, A0, A1, A2, have multiple members, multiple physical members. Now, I have ISIS enabled, and each one of these interfaces, A0, A1, AE2, are configured under protocols ISIS, and they have the same cost, the same metric. So from the point of view of ISIS, these are 3 different paths or 3 different links with the exact same cost. So if I turn on ECMP, if I enable load balancing, as I showed you in the previous example, there's going to be equal distribution of traffic across these 3 lag interfaces. Now, what if one of the interfaces, let's say that within AE0, one of the physical members goes down? Well, ISIS is not going to see that. It's not going to start, as long as the AE0 is up, ISIS is going to treat it as another link with the exact same cost. So I need to make sure that ISIS, or not ISIS, but the load balancing process can see that AE0 now has less bandwidth than AE1 and AE2, and then distribute the traffic accordingly. So that's when I enable weighted ECMP. So it's just a matter of adding these commands to our configuration. We're gonna do set protocols ISIS, SPF options, multipath, weighted 1 hop. This only works for, when I have directly connected neighbors that have these kind of set up. All right, so after I set it up, again, the traffic is going to be distributed according to the actual bandwidth of each one of these links. All right, so next one that we're going to talk about is EBGP. And actually, the first part of this section applies to IBGP as well. And we know that BGP doesn't have load balancing by default, just like the other protocols. But not only that, load balancing is not possible by default, even if you have ECMP turned on, even if you have that policy applied to the forwarding table. The reason for that is the way BGP selects the best next hop, the best route for a particular prefix. So this is BGP itself making a decision before the route can be considered by the routing engine to become active and be used for forwarding traffic. So the way that BGP makes this selection is by comparing the different attributes. So it's going to go through local preference, AS path, origin, and so on. And at the end, it's going to choose one and only one, even if it has to go all the way down to checking the IP address of the neighbor that it's sending the route. So the result of this BGP selection process is one and only one next hop available for forwarding traffic. So that's why even if you turn on ECMP, it doesn't do load balancing because basically there is only one next hop per route in the routing table. All right, so in order to turn on BGP load balancing, there's two steps. The first one is make the multiple next hops available for load balancing. Make sure that the routing table or the route in the routing table has 2 or more next hops. And then when you turn on ECMP, load balancing can be implemented. How do you do this, or how do you complete this step? It's going to depend on the case. And I'm going to show you the different cases that you may run into. All right, so excuse me. It's basically going to be, some of them are going to be using multipath. Some of them are going to have multi-hub. So multi-hub is not really load balancing, but you're going to need multi-hub if you're using, for example, the loopbacks in EBGP. And the result of this configuration is that 2 or more possible next hops are going to be active in the routing table and can be considered for load balancing. At that point, you can enable load balancing, you can turn on ECMP, and the result is that those next hops that you made available on the previous step are now going to be in the forwarding table. So let me talk about the different, let's say, cases or scenarios that you might run into or that you might want to implement. So the first one is a situation or a case where you have 2 different routers with 2 physical interfaces connecting them, and you're going to be setting up 2 BGP sessions using the physical interfaces. All right, so in this example, we'll have a BGP session between 10.10.1.1 and 10.10.1.2, and another one between 2.1 and 2.2. That means that router 1, it's going to be getting 2 routes for the same destination. And in order to make those 2 next hops available for load balancing, you're going to turn on multipath. Now, what is this doing? Let me go back to that decision process. Basically, it's telling the router not to check EBGP, whether the route was received before, not to check the router ID, not to check the peer IP address. So it's basically stopping the decision process before it goes all the way down to lowest IP address. So I can have those 2 next hops available. They still have to be have the same local preference, the same AS path length, origin, med. They have to be both EBGP, IBGP, but I'm not going to look at the router ID, for example. All right, so in this case, we're going to need multipath to make load balancing possible. There's no next hop. I'm sorry, I don't need multi-hop because I'm using the physical interfaces. Multi-hop is only needed if I am configuring EBGP between the loopback interfaces. If you were here for my presentation yesterday when we were talking about the next hop, EBGP verifies that the neighbor is directly connected by default. Multi-hop disables that verification so that I can peer between the loopback interfaces. All right, so there's really not much difference between this and this. Well, actually, there's a lot. I'm kind of jumping ahead of myself. The difference here is that this one is just two EBGP sessions behaving the normal way. This is between loopbacks, so multi-hop is needed. Now, the other detail about this topology, about this option is the next hop of the route, and I'm only getting one route because there's only one session between these two routers. The next hop of that route, it's going to be 192.168.2.1. Let's say that VR2 is advertising a route to router 1. So the next hop is going to be 192.168.2.1. So how is the load balancing going to happen? Well, if router 1 receives this route and tries to resolve the next hop, the BGP next hop, 192.168.2.1, it resolves to two physical next hops. In this example, I have static route. So when the route is installed in the routing table, it will have two next hops available. So all I have to do is turn on ECMP for load balancing to happen. Now in this other example, or these two other cases, I have two neighbors. So I'm going to be receiving two routes. So if I'm receiving two routes, I'm going to need multipath to allow load balancing to happen, so that the two next hops are available. All right, so every time you have two neighbors, three neighbors, multipath is going to be required. Now this option uses the loopback, this option uses the physical interfaces, so this one also needs multi-hop to be configured. And this one, it's basically two neighbors, but they are in different autonomous systems. So we are we're going to need multipath, multiple AS to allow load balancing to happen. By the way, multipath, multiple AS, it's going to be configured on the receiving side. So if this router receives routes from router 2 and 3, configuring multipath, multiple AS on router 1 will allow router 1 to load balance traffic going to those different ASs. So I'm going to show you examples of some of these cases. I'm not going to go over every single one of them. So case number one is the case where I have two BGP sessions, and that means we need multipath enabled. So every time you have two neighbors, or you're receiving two routes with two different next hops, you're going to need multipath configured. No multi-hop because we're not using the loopbacks. So here's the configuration, nothing special about this. I have a BGP session between the two, an EBGP session between the two. Actually, two EBGP sessions between the two routers. There's two neighbors on each side. So here is how the route looks like before I turn on multipath. So you see, I'm taking a look at the routing table. So route 200.1.1.1/32 is the route that, is this route that it's being advertised by my neighbor. And when you look at the routing table, there is actually two routes. One that I'm receiving from 10.10.11.2 and another one that I'm receiving from 10.10.21.2. On your, in the actual output, when you type the show route command, this is not going to be displayed. But it's basically implicitly telling you that this is a route for the same prefix. It's easier to see it this way, so that's why I added this. So out of these two routes, the first one is the active route. And that means this is going to be the active next hop and the next hop that you're going to have in the forwarding table, which you can see down here. When you do show route forwarding table, you only see that. Now, why was this route chosen over this route? You can take a look at the show route extensive command, and there's going to be a line that specifically tells you why the route was selected. In this case, update source. So it's looking at the actual address of the neighbor to make that decision. It's going all the way down to that very last step in the BGP decision process. So I enable multipath. In this case, I did it on both VSRX1, VSRX2, but you actually just need to do it on the receiving side. So after I configure multipath, I type the command, the show route command again. And what you're going to notice here is that I still have those two routes. The first route is still the active route, but now that route that it's active has two next hops. It's basically, what the router basically does is copies the next hop of the route that it's not active into the route that it's active. So that the active route now has two possible next hops. You can also do extensive and see how the active route has two next hop available. However, only one of them shows selected. And in the standard output, you have that greater than symbol. When you look at the forwarding table, there is still one single next hop. So multipath is basically the first step that you complete for enabling load balancing in BGP. Is making the two next hops available for load balancing. Now we need to turn on load balancing. So just like we did for OSPF and ISIS, we just need to apply the policy to the forwarding table. In this case, I just activate the policy that I deactivated before. And this was already enabled. Now, the difference is going to be on the forwarding table. You're not going to see any changes in the routing table. When we look at the forwarding table now, there is two next hops installed. Actually, you can see that the two next hops that were part of the active route are now on the forwarding table. So load balancing can now happen. So in case number two, basically, instead of having two BGP sessions, I have a single BGP session. And it's between the loopback interfaces. It's going to need multi-hop, just because the BGP session, the EBGP session won't come up if I don't do multi-hop. No multipath is required because I only have one route. So I really don't need to choose between two routes. What I need to do is make sure that the next hop, the BGP next hop, can be resolved to the two physical addresses, the two physical next hops. And in this case, I'm just using a static route. Very unlikely I'm going to be running a routing protocol between these two devices. An IGP between these two routers in two different ASs. So it's basically going to use a static routing. So here's the config. So multi-hop was added to make it work, and also the local address. because I'm peering with my neighbor's loopback and I need to use my loopback as the source address of the traffic. So I also need that command. So here's how the routing table looks like. So without me having to do anything special or enable multipath, each one of the routes is going to have 2 available next hops. This is how the forwarding table looks like without the policy applied, and this is how it looks like with the policy applied. Now, this case is where you have 2 next hops or 2, let's say, neighbors. So multipath is required to make this work. Again, you're getting 2 routes. You need to choose between those 2 routes. You're telling your router, no, don't choose. I want to use those 2 next hops for load balancing. All right, so you see that the routing table only has 1 next hop before you turn on multipath. Then you go ahead and turn it on. Now you have the 2 next hops. And if you turn on ECMP, you're going to see the 2 next hops in the forwarding table. So it's very similar to the first case, except that instead of 1 physical neighbor, I have 2 physical neighbors. Now this one is, I'm not going to go over the details of this one because it's pretty much the same as this, but I need to add multi-hop to make my BGP sessions come up because I'm peering with the loopbacks. Number 5 is when I have 2 different neighbors on 2 different ASs. And I want to be able to load balance between the routes that I'm getting from both. So in this case, I need multipath, multiple AS. So the command has these 2 different keywords. So here's my config of BGP. Here's how my routing table looks like before I apply multipath. And then I enable that multipath, multiple AS. If you don't add multiple AS to your command, if you just type multipath, it doesn't work because the routes are coming from different ASs. All right, so after you configure that, you see the same results that we have been seeing. I have 2 possible next hops within the active route, and those 2 next hops are in the forwarding table. And obviously, this is because of the policy being applied to the forwarding table. This one is the same, but I need to add multi-hop to make the sessions come up, so I'm not going to cover this. Now, IBGP have similar cases, but probably the one that you're going to use the most is this one right here. The main difference is that because this is not EBGP, you don't need multi-hop. So even if you use the loopbacks, no multi-hop is needed in any of the cases. So it's basically similar cases. I'm not going to show you the actual configurations for these ones, but it's a similar behavior. So once again, every time you are receiving 2 routes with basically 2 next hops, you're going to need multipath enabled. All right, the last thing that I wanted to talk to you about is EBGP bandwidth multipath. And this is the idea. By default, when you enable BGP multipath, as we just saw, traffic is distributed equally among all the available next hops. Remember that BGP does not take into account bandwidth or cost associated with the bandwidth, like OSPF or ISIS do. It uses local preference, MED, whether the route is EBGP versus IBGP. Those are the things that BGP takes a look at or compares. So there could be a situation where I have 2 routes that from the point of view of BGP are equally good because they have the same attributes, but the bandwidth is not the same. So I would like to be able to distribute the traffic based on that actual bandwidth. So I can use this feature, BGP bandwidth multipath, which enables distribution or the distribution of traffic between paths with different bandwidth. Now, in order to make this work or make this happen, the routes are going to be tagged with an extended BGP community, a bandwidth community, which encodes the bandwidth of a given next hop. And when you have that community configured, when you have the route with that community, and you also have multipath and load balancing enabled, then you can start balancing traffic or distributing traffic proportionally based on the bandwidth. So they give you an example here where I have two different paths, one with 10 megabits per second, the other one with 1 megabit per second. And if I am using this extended BGP community, the router will be able to send 9 flows out of the 10 megabit per second and 1 flow out of the 1 megabit per second. So it distributes them basically proportional to the relative bandwidth between the two, or the ratio between the two. And also when the BGP multipath operates among routes that contain the bandwidth attribute, or actually the way that this is implemented is the forwarding engine now has that information, and it's going to distribute the traffic based on that information. I'm going to show you an example of how the routes look like. So one little detail, you have to make sure that, in order for this to work, all the different paths that you're basically taking into account or considering for forwarding traffic, all of them need to have this bandwidth community. If you don't have all of the routes with the bandwidth community, then this doesn't work, right? And the way that you're going to configure this is pretty much the same things that we did already. You need multipath, you need equal cost multipath enable, the policy applied to the forwarding table, but you also need to label the routes with the community. So that community is defined by this document, this draft document. It's an optional non-transitive attribute. And here's the format of that. It's bandwidth, column, the autonomous system number, the local autonomous system number, and here is the bandwidth of the interface. So you are going to configure a policy, apply that policy in the import direction. So the routes that you received from your peers, from your neighbors, are going to be tagged with these communities. And once you have that, and again, you have ECMP enabled, you have multipath enabled, the router will take into account this bandwidth to, distribute the traffic. I don't have this in my lab. I'm planning on adding that to my lab soon, but I can show you an example out of Juniper's website. So here's the topology. It's actually very similar to what I have in my lab, so I should be able to implement this in my lab. So the idea is, again, these two interfaces have different bandwidth, and I want to be able to distribute traffic proportional to that bandwidth. So here's the config. So notice that they have a policy that adds a community to the routes. Add BW-high is the name of the community. So bandwidth high, and there's a second term that for the second next hop, so basically for 10.0.1.1, I'm gonna add this community. For routes coming from 10.0.0.2, I'm going to add this community. 10.0.1.1 and 10.0.0.2 are these two next hops. Now the communities are defined down here. And notice that they have that autonomous system and then the bandwidth. Also, I have my policy, where is that? Right here. So the policy that says front route filter 10/16, then low balance per packet. So I'm going to be implementing low balancing for traffic going to this network, which has been advertised to me by router 2 and router 3. And in order to make that work, we are applying the policy as an export policy to the forwarding table. All right, so once that is configured, we can take a look at the results. And notice that if I look at the routing table, show route 172.16, that should actually be 10.016. Here is how it shows the proportions, the percentages that will be sent, the percentages of traffic that will be sent to each one of the next hubs. So this 40%, 60%, it's based on these values that I added to the communities. All right, so hopefully that gives you a good idea of how this feature works. And I've been hearing about this a lot lately from some people. I don't know if you guys have any experience with it. So that's basically what I wanted to show you today. So again, I thank you for attending the Juniper session, and come back for more videos on our next expertise session.